All right, let's continue with the last talk of the workshop. So we have Itamar Vigdorovich, who's going to speak about many Hilbert-Schmidt stable amenable groups.
Yes, thank you very much. I want to first thank personally for inviting me to talk on this conference. It's really a pleasure. And also, this is the last talk of the conference, so I think we should thank the organizers for this great conference. I also feel like I need to thank Tatiana for preparing my talk so well, and also in a sense preparing my PhD in such a well, because a lot of my work is based on your work or inspired by your work. So the general, I don't think this is a title I wrote to this, but basically this is really the theme I want to talk about, that there are many Hilbert-Schmidt stable amenable groups. This is a joint work with Alon Dogon and Ariel Levit. One work is only with Ariel Levit and another work is with both. So let's just recall the definition of Hilbert-Schmidt stability. So a group G is Hilbert-Schmidt stable if any approximate representations are close to actual representations. So let's recall, what does it mean that they're approximate representation? It means that when we check this homomorphism relation, it asymptotically vanishes. This is here in the Hilbert-Schmidt norm, and this happens locally. So for each G and H separately, we have this limit. And what does it mean that those FNs are actually close to real representations, to actual representations? So here it means that Fn G is close to phi n G. Once again, this is true for each G separately. And of course, these phi n are really our representations, and those Fn are just maps. So maybe I'll just remind that if X is a unitary, then this is by definition, we normalize the trace norm. By the way, this is also the same as this Euclidean norm. So this is the norm. And so let's give some examples. Examples of Hilbert-Schmidt stable groups. So the first example is, of course, free groups. I'm, of course, repeating some stuff that were said before, but just to prepare things right. So free groups are, of course, it's very easy to be a homomorphism from the free group. Actually, also virtually free group, but then this is a theorem by Mova and the next example, not chronologically, but I'm just is z squared. This is a result by Glebsky. This is of a more like classical flavor because it has like a very classical questions of two almost commuting matrices, or they're close to commuting matrices. And let's talk about non-examples too. Okay. So there's this nice example of Joanna. Another thing that was mentioned in the mini course. So if you take a hyperlinear group, or what's called a Cohn's embeddable group. So if it is hyperlinear, means I can approximate it by almost representations to the unitaries. And if I have stability, then I can fix them to actual representations. So hyperlinear plus stability will imply you are maximally almost periodic. So I'll just say it though, hyperlinear, but not maximally almost periodic. These are examples of non-stable groups. And it's actually a way to perhaps try to find maybe a non-hyperlinear group. I want to also write some notable unknown examples. So maybe here I'll first write one more. This is infinite groups with property T. This is Becker and Lubotsky. However, it's worth mentioning that if you look at their proof, it's like a it's very delicate. And I'm not going to repeat what's the definition of flexible stability. I'll just remind that it's when you allow a bit more flexibility with the correction, that those phi n don't need to be in the exact same dimension as the almost representation. It can be slightly larger. And then, of course, you need to compare them. So this doesn't mean so this result in particular doesn't mean that those groups are not flexibly stable. And in fact, the proof of why they're not stable suggests, in a sense, the definition of this flexible stability. And in fact, here are notable unknown examples. So consider this property T group. So this is of flexible stability. So consider, for example, SP, the symplectic group, integer values. Or so G will be this, or G is a random, a Gromov random group. So there's a way to randomize groups, and then there's a certain realm where these groups are almost surely have property T. And there's a nice, very recent result of Dogon, Alon Dogon, is that G, if you show that G is flexibly Hilbert-Schmidt stable, and in fact something weaker than that. It's called a weakly UCP, flexibly stable. Those names are hard to remember. Then exists a non-hyperlinear group. It's actually not exactly that group will be hyperlinear, but some closely related group. So this is another way in which stability is very related to hyperlinearity and approximation properties. But as you see, there aren't many examples, known examples here, and as well as non-examples here. And indeed, it's very hard to show that groups are stable. It's like there's no general theory to how to attack each group. You kind of do it separately, but then the nice theorem that really gives you a characterization, that gives you some new tools, is this theorem by Hadwin and Schulman. Says the following: an amenable group is Hilbert-Schmidt stable if and only if every character is a pointwise limit of finite dimensional characters. And this is something you can more easily work with. Maybe I'll just explain what I mean by characters. There are different terminologies. I'm going to use the terminologies as given in the mini course. So a character on G is a function phi complex valued function, which is positive definite. It's a class function, conjugation invariant function. And also we add this normalization. And since this is an operator algebra conference, I'm sure you know this definition also as this definition. So every character of G extends uniquely to a trace on the C-star algebra. And so this is a simplex. It's a compact convex set, and moreover a simplex. And inside this space, we have this, so let's just identify them. We have this space that I call finite dimensional characters. So these are basically characters that they're GNS, that if you do the GNS, you get a finite dimensional representation. And this is, you can check that this is a face. So we have this simplex. And then every C-star algebra has this simplex and has this special face. The question is, so the property that is discussed is so let's just say it as a property, so G, just write it here, character, so i.e. the face of finite dimensional characters is a dense face. So actually this property is, I think, interesting on its own. For example, if you take G to be the free group, having this property is equivalent to the Con's embedding problem. Of course, this doesn't contradict the theorem. The free group is stable, but it doesn't contradict the theorem because it's not amenable. But so for the free group, it gives that property. For amenable groups, it's related to stability. Maybe for other groups in C-star algebras, it means other things. In any case, this is the property. And once you have this property, you can easily get new examples. So one example is, of course, virtually abelian groups. And this is an immediate corollary because virtually abelian groups, all the characters are finite dimensional. You don't even need to take approximations. But it's funny because even if take like a finite group, I'm not. Yes, the extreme ones. You're right. But yeah, it's enough to show for that extremal points can be approximated. So even if you take a finite group, try to show that finite groups are Hilbert-Schmidt stable. I'm not sure how to do it without going through this theory, actually. But there should be, I think, a much easier proof, I guess. And another example is the Heisenberg group. The same authors. There's also a nice example by Schulman and Eckhart. What's interesting about this example is that this group is not stable in permutations. So it's a nice example of a group of some separation between the stability when your target groups are permutation groups. So maybe I should also write in the notable unknown examples permutation stable groups. So are permutation stable groups necessarily also stable into matrices in the Hilbert-Schmidt norm? Maybe I'll also here write another one is surface groups. Whether fundamental groups of surfaces have this property. So I was working a lot about characters until I heard about this criterion, which kind of allowed me to study stability without really knowing what it means. So I restrict only to the amenable case because that's the case where we can use characters. The results are the following. So the first result and I'll just state some of the groups we know how to show that are Hilbert-Schmidt stable groups. It's not a complete list. So the following groups, the following amenable groups are Hilbert-Schmidt stable. So Lamplighter groups, but in fact, more generally, whenever you take a finitely generated abelian group and you take its Ritz product with any abelian group, this is fine. Solitar groups of this type, virtually nilpotent, finitely generated, virtually nilpotent group. And as was mentioned by Tatiana, the nilpotent group was actually established independently by her and Eckhout. So I'm going to be a bit rough, but upper triangular matrices groups with certain rings coming from certain number fields. Not all number fields, I know how to show this, but for some number fields. Another maybe interesting example is the free metabelian group. So the free metabelian group is, you take the free group and you want to make it metabelian, so you take its derived subgroup and then you take again its derived subgroup and you quotient it. This is the universal metabelian group generated by n elements. And maybe another one is any group of this form will be Hilbert-Schmidt stable. And this uses dynamics. And I will explain later about it. The second theorem which maybe more justifies the name many, the word many, is that there are 2 to the aleph naught Hilbert-Schmidt stable groups So which kind? They are all generated by two elements, and they're all amenable. So what I want to do is to explain whether these groups describe their interesting structure, not say much about the proof, but I think once you just get into the structure of the group, it's interesting on its own. And then, if I'll have time, I'll also talk about how all these results, which these are all solvable groups. In solvable groups, you can really more use dynamics because you have like a lot of abelian normal subgroups there. So there's a lot of like dynamical data hidden there that you can use. So this leads me to talk about the BH Neumann groups. So these are groups constructed by BH Neumann. So first, let's fix some notation. So if X is a set, I'll use this to denote finitely supported even permutations on X. And another notation is if R is an integer, I'll use this notation to denote the set of integers between R and minus R. So in particular, we have these groups. This is a finite simple group, just the ordinary alternating group for R at least 2. Now, in order to construct the BH Neumann groups, well, basically the idea is that all those groups for different R's are non-isomorphic. Each group is of different cardinality. And also, if you'll take different products of such groups, infinite products, it will be determined just by the, so if you take a set of indices, set of natural numbers, let's say in ascending order, then you can look at this product. And it's easy to see that if you take different J's, you'll get different groups because the components are different. But these are, of course, not finitely generated, so it's not, so what we're going to do is we're going to choose here 2 elements. So the first element will be sigma, or tau. Let's start with tau. Tau is like a transposition. It's a small element, so tau will be, well, of course, it's a product of elements, and it will be, and tau I is just the following permutation, viewed as an element of Ri. And the other element is a shift. So sigma I will be just the full shift on the appropriate group. And the BH Neumann group is just the group generated by sigma and tau. So the BH Neumann group corresponding to the set J is, by definition, this finitely generated group. Now let's try to understand just a bit the structure of this group to get some idea of what this group really is. So first, let's define Nj to be, let's take this element tau, and let's take its normal closure. So clearly, we have this short exact sequence. And when I quotient by this normal closure, I'm left with this sigma, which is isomorphic to Z. So of course, this splits. So first of all, just let's note that this group is a semi-direct product of Z with Nj. So we should understand N a bit better. And I want to claim that N is a locally finite group. How do we see this? So I want to kind of try to get a more visual picture of N. So this is the first alternating group. The second one is slightly larger, and this is larger, and this is larger. And we have this element tau, which is just a small permutation. What happens when we start conjugating tau by the other element, by sigma? We start moving this permutation. When we conjugate just in this group by the full shift, we just move this orange thing up or down. But of course, we do it all diagonally. So imagine I do it for, I don't know, 3 times. I conjugate it by sigma 3 times, and maybe also backwards 3 times. So I reach at some point, I'll probably, if this is small enough, I'll probably fill all this out. So I'll surject onto this group, and maybe also onto this group. But at some point, of course, I will not reach till the end, and I'll get this kind of cylinder with some kind of diagonal embedding there. Now this group I denote by Ln. So Ln is the set of elements of x1, x2 till xn, and then I just repeat xn, xn all the way. Xi is in alt Ri. Okay? So this is actually a finite group. It says this group is isomorphic to the finite product of those finite alternating groups, but it's embedded each time. So so I want to say that this N is a locally finite group, but in a quite interesting way. So every time we take a larger and larger product, but the embeddings are each time I kind of take the last element and I copy it to the next element too. Okay, it's not too important exactly the full details, but the point is that this should prove 2 things. So let's conclude this. Conclusion. The BH Neumann Weizmann group corresponding to the set J is Z by locally finite. So in particular, amenable. Is of course 2 generated by definition. And the last thing to note is that if one index, for one index set, and now we choose a different index set, and suppose we got isomorphic groups. So if they're isomorphic, also their commutator subgroups will be isomorphic. And it's not hard to show, basically from what I wrote here, that this is the commutator subgroup. So if Gj and Gj prime are isomorphic, then Nj equals Nj prime are isomorphic. And now these N's, these are sequences of elements which are at some point constant. Inside of them, you can ask what are the torsion elements. The torsion elements are exactly where eventually it's 0, or the trivial element. So this will imply that the torsion of Nj is isomorphic to the torsion of Nj prime. And the torsion elements are exactly those that are actually finitely supported in the sequence. So this is the direct sum of those finite alternating groups. And here it's J, and here it's J prime. And this, of course, implies that J equals J prime. So this is a family, indeed, of uncountably many. So these are, i.e., the BH Neumann groups. For the proof, it's actually very different. It's in a sense orthogonal to proofs of like what I just erased about the solvable groups. Because I think usually when you try to show, let's say, a C-star algebra maybe has a unique trace, or you want to understand characters of a group, at some point maybe you'll want one group acting on some space in a very free way or very outer way, and that will kind of imply that it has to be 0 outside. This never happens for the BH Neumann group. So everything in this group is very inner. The actions are, even if you take like a group, take G, and it acts on this normal subgroup N, well, of course, the action is not inner, but it's locally inner. So at every window inside N that you look at, and you look at this action, it will look like as if it's inner. So kind of like all the general methods you want to enter to understand traces of a group or of a C-star algebra, you don't really have there, and you need to use other things. What we use is character theory of finite simple groups. These are results of Larsen and Shalev that give you all kind of very concrete bounds on the size of the character table, how many of the numbers in the character table, and we use this to understand the characters of the BH Neumann groups. Yeah, I'm sorry, I didn't mean torsion. I meant. Thank you. That's I'm sorry. That was a mistake. Oh, okay. Yeah. So I mean the elements with finite conjugacy class got mixed up, but thank you. So now in the rest of the time, I want to talk more about how to use dynamics to get new results about solvable groups. And these ideas are actually also appear in the work of Schulman and Eckhart, and I want to explain more how to you really use dynamics to get new results. So here's the basic idea before I go just straight into definition. So you have a group G, and you want to understand its characters. You want to show basically that every character can be approximated by finite dimensional characters. Now let's assume here that G is amenable or maybe even solvable, because you don't have to, but it will be more relevant. Because when you have a solvable group that you want to understand, you're very likely to at some point use some normal abelian subgroup, which necessarily exists. So what you can start doing is to restrict this character from G to N. Now this is an abelian group, so traces or characters in N or traces on its C-star algebra, this is in one-to-one correspondence with probability measures on the Pontryagin dual of N. Or in other words, states on this commutative C-star algebra corresponds to probability measures on the Pontryagin dual. But now, traces, the characters of G are obviously conjugation invariant by definition. So when I restrict, this is the restriction map, to N, I'm still conjugation invariant for the G action. So what I should write here is not just characters of N, I should write characters of N which are fixed by the conjugation action of G. And therefore, I should do the same here. So already I get this kind of dynamical system. G acts on the dual of N, and you need to understand something about probability measures. The finite dimensional characters under this diagram will correspond here to finite dimensional characters of N, which are G invariant, which will correspond to probability measures on the dual of N, which are measures, these are measures with a finite atomic support. Okay? So the conclusion is that if this is dense here, then this is dense here. So this motivates the following definition. So you have a group G, and it acts on some compact space by homeomorphisms. So this dynamical system is said to have dense periodic measures if every probability measure of G, which is invariant, every probability measure on X, which is invariant under the G action, can be approximated by those finitely supported measures. Thank you. Now the question is, which kind of dynamical systems have this property? So I want to now propose like a general strategy. So showing dense periodic measures. It's a general strategy, but we'll see that in a sense it's the only strategy. Well, first, if you want to show you have this dynamical system and you want to show that every invariant probability measure can be approximated in the weak star topology by such measures, of course, we will start with some probability measure, some arbitrary G invariant probability measure. And without loss of generality, it is extremal. It's an extreme point or ergodic. Now, since it's ergodic, we can use the Birkhoff pointwise ergodic theorem. So Birkhoff says the following, that for mu almost every x, we can on the one hand take these measures. So let's assume for a moment G equals Z. It's just generated by one single homomorphism of x. Everything works here also for amenable groups because you have these appropriate theorems for whenever the group acting is amenable. But just for simplicity of notation, I can take here this x, this generic x. I take the Dirac, I apply k times the transformation on x, and I take here this average, and this will converge to mu in the weak star topology. So this is already, in a sense, like we didn't do nothing. It's just a general system. We already got, in a way, quite close, because we have this kind of finitely supported measure where each time it's the iteration of the previous point, except that we don't end up back in the point we started with. But we can use Poincare recurrence. So you start with this point, and you apply t to it, and you apply t again, again, and eventually you'll return very close to your point. So what you're left to show is that your dynamical system has this property that I'll call orbit stability. So what is orbit stability? I'll just say it roughly. Every almost orbit or approximate orbit is close to an orbit. So it's funny because we started with a problem with stability. We used the Hadwin-Schulmann's criterion to kind of move away from stability to an approximation property of characters. We went to the dynamical systems. We got an approximation property of a dynamical system. In order to solve it, once again, we need to solve a stability questions of something almost being satisfied. Can you correct it to being satisfied? And this properties, I would say this like world of properties, it's actually as in hyperbolic systems tend to have those kind of properties. So there are actually extremely strong properties called specification in dynamical systems that really allow you to, you kind of choose any points you want in your space, and specification will tell you that no matter what points you specified, you can find a periodic point which will kind of track all those points or almost all those points. So let's just give one example where we can show that a very simple example. So all of the Lamplighter group, the Baumschlag-Solitaire group, the free metabolite, all those examples use this kind of idea. But I want to give the most simple version is the Bernoulli shift. So the Bernoulli shift, we have Z, and it acts on a finite alphabet, let's say 0, 1, and it acts by the shift. And if you studied a bit this dynamics, you might have encountered what's called the orbit closing lemma, which basically says what we need, what you want to show. So how do elements here look like? They look like infinite sequences. And now we have an almost periodic element. We want to show that every almost orbit is close to an orbit. So you have an almost periodic element. What does it mean that it's periodic? Means that periodic means that after applying the shift finitely many times, you get the same thing. So it's actually a periodic string. Being almost periodic means that if you look at a very large window, it seems as if it's periodic. But since it's now on such a large window the same, what you can do is just basically do copy-paste. You can copy this window and erase whatever's written here and just put this window again and again. In other words, what I'm trying to say, it's very easy in the Bernoulli shift to make things periodic. You just copy-paste whatever you want to be periodic. So in other words, this is orbit stable. And therefore has dense periodic measures. And with more work, which I will explain in a moment a bit more, is that the, for example, lamplighter groups are Hilbert-Schmidt stable. So this part I think I explained, but it's not clear how you go. I only showed one direction. I said that if your group is stable, then those dynamical systems will have this property, not the other way around. So for that, I want to kind of to conclude, instead of going through all the examples, to kind of conclude in this following table to demonstrate the picture we have about stability of solvable groups and the relation to dynamics. So here we have questions about groups. Here we have questions about dynamical systems. Here we have a stability property. And here we have an approximation property. So here we have this property of G being Hilbert-Schmidt stable. And since we're restricted only to the amenable case here, so G is amenable, this is equivalent to finite dimensional characters being dense in the space of characters. And what I explained before is that if you have this property, then when you look at this dynamical system, it has dense periodic measures, and this is true for any normal subgroup of G, which is abelian. And as I said, the way to show this is by orbit stability. So G is orbit stable. Once again, for any normal subgroup, abelian normal subgroup. What we now want to do is to make those arrows more two-sided. So the easy part is the following. This orbit stability, if you think about it, it's much stronger than we need. It's like really tracks the points, but actually what you need is a more statistical version of orbit stability. You don't need to correct your almost orbit to just uniformly to an orbit. You need it just kind of statistically to be true. So there's a notion we call weak orbit stability, or we call it, I think, in the paper, Weiss approximation. But once I put here weak orbit stability, which is actually the more suitable one, you get an equivalence here. At least if your group is residually finite and finitely generated. Now, what about this one? This is a more interesting one. And this is true if G is monomial. I'll finish in a second. I'll just say that once we have this, of course, we have this whole table. What is a monomial group? So this is already in finite groups. You have this notion of monomial groups. These are groups that every representation, irreducible representation, is induced from a one-dimensional representation of some abelian subgroup. So we extend this notion to infinite groups, and we call it almost monomiality. The idea is the following. As I said, if you have this property, you have this property. But if you want to show from this property, you need to some information. You need to say something like all the characters of G are somehow controlled by these normal abelian subgroups. This is exactly what the monomiality ensures. It ensures that all the character theory will be, it's enough to study such dynamical systems. And so maybe the theorem that we proved is that metabelian groups and as well as polycyclic groups, some type of solvable groups, are monomial. So at least for this class of groups, this whole square is complete. So the lamplighter group is stable because the Bernoulli shift has those stability properties. The same is true for the Baumschlag solitaire groups with a bit more work and the free metabelian group. For Z semi-direct product Zn, what you're led to study is, of course, the dynamics on torus. And then you can use other known results and use hyperbolicity to show this kind of orbit stability. Yeah, I think these are the main examples that kind of I want to mention here. That's it.